Welcome, everyone, to our November RAS Public Talk. It's so good to have you here. Today's talk is entirely online, and we do intend to be back at Burlington House for our December event next month. And it will be a hybrid talk, so we'll be happy to welcome you back to Burlington House. Hello, I am Lucinda Offer, your RAS Public Talk host, and one of the Education Outreach Officers at the Royal Astronomical Society, where we encourage the study of astronomy, geophysics, and space science. And for today, we have a wonderful and exciting guest speaker to share with us their research on cosmic dust. Professor Haley Gomez is a professor of astrophysics at Cardiff University. She studies the formation and evolution of cosmic dust using space telescopes, including the Herschel Space Observatory and James Webb Space Telescope. She has recently been appointed as the head of the School of Physics and Astronomy in Cardiff, and she was awarded an MBE in the 2018 Queen's Birthday Honours. She gives regular public lectures and has been featured at the Royal Albert Hall and National Museum of Wales, as well as in the Sky at Night magazine and Astronomy Now. She has worked with charities and appeared on the science podcast BBC's The Life Scientific with Jim El-Khalili, and was also a speaker at the 2015 TEDx Cardiff, where she discussed the origins of life. It is wonderful to have Professor Gomez with us, and we are looking forward to hearing about her work. But before we begin, we want to let our audience know that we are also live streaming on YouTube. Apologies if you hear my cat, and can take questions from there as well as within Zoom. So please get your questions ready for after Professor Gomez's talk. You can use the Q&A on Zoom and the chat box on YouTube to post them. Thank you again to everyone for being here. And thank you, Professor Gomez, for being with us today. On to you. Hopefully you can't hear my cat.
Thank you so much, Lucinda. Thank you for inviting me. Let me just share my slides and hopefully you can see that.
Yes, all good.
All good. Great. Thank you. That's what we like to hear. Okay, so today I want to talk to you a little bit about the research that I am passionate about, research into cosmic dust in the universe. Hence my title, Ashes to Ashes, Dust to Dust, a search for the stolen starlight. So hopefully that will become clear as I go through the talk tonight. So first of all, what do I mean by cosmic dust or space dust? Well, or stardust, the different terminology for it. Well, when we use those terms, we're not talking about dust in our own homes. We're not talking about dirt and bits of dead skin and so on. What we're talking about is a particular form of the material between stars, solid particles. And so here are a couple of images through a microscope of some dust grains that have fallen to Earth. One fell to Earth and one was collected in the tail of a comet. And what you can see in these images is that these things are very small. Dust grains are actually quite small. There's a 1 micron kind of scale size there. So this whole thing is probably about 25 microns in size, and that is very, very small. Kind of talking about the width of a human hair, a little smaller than the width of a human hair. So we're talking about very small particulates in space, and these are mostly made of silicate material, carbon. We do see a lot more of the other elements in there, iron, silicon, magnesium, things like that. So we are referring to tiny little rocks in space when we talk about cosmic dust. And one of the things that we think about with cosmic dust is illustrated in this photograph of downtown LA. So what you can see in this image, or what you can't see in this image, is the very distant skyscrapers in LA, and that's because of the smog, the pollution that is in the atmosphere means that we can't see very much detail far away. And I want you to think about the space dust being very much like smog. So as we see in this picture, space dust is the right size and made up of the right materials that it basically blocks out visible light from interesting astrophysical sources. So it effectively makes our universe a smoggy place. And that can profoundly affect the way that we view our universe, distant galaxies, and even objects in our own Milky Way. So when we think about this is obviously on Earth. This is not astrophysical dust. This is just pollution in our own atmosphere. But when you look at the night sky, this is an image taken by a famous photographer, Babek Tafrashi. This is not an image or anything like this. That you would not be able to see this from Cardiff. We just basically can see about 3 or 4 stars in the night sky. But if you are lucky enough to go to a dark sky in the world, you'll be able to see this beautiful sight of our own Milky Way galaxy. And a long time ago, lots of astronomers at the time did not really understand that these wisps of black that you see here that very much look like smoke, they did not understand that that actually wasn't due to the absence of stars, and it was in fact due to the presence of cosmic dust. So across our entire galaxy, cosmic dust blocks out our view from a lot of starlight and a lot of interesting physics that we can't see through. And this is why dust was seen as a nuisance, or is still seen as a nuisance actually to astronomers. If you're trying to recover starlight, dust blocks it out and gets in your way. And it's not only in our galaxy that we see this in nearby galaxies. So here we have an example of interacting galaxies on the left and an elliptical galaxy on the right. And in both cases, you can see the stars that make up that galaxy, but you can also see this giant band of dust emission. And you see this giant band of dust emission because it's blocking out the light behind it. We're not observing the glow from dust. We just see the fact that it's blocking out the starlight behind it. And this is quite incredible because we're talking about very small particles in space, a couple of microns across, and yet it makes an effect that extends hundreds of thousands of kiloparsecs across a galaxy. So acts on enormously large scales, despite being an incredibly small thing. And in the case of the elliptical galaxy here, the dust grains actually hint that there's something very energetic happening behind that dust screen, something we now know to be a starburst phase, where there's so much energy being chucked out, so much of this dust is chucked out into the edges, and it kind of looks like the smoky remnants of a fire. So dust grains tell us something really unique about galaxies. They can hide information, but they also hint at something going on. For example, we know that star formation is enshrouded within clouds of dust. So looking for dust grains can also help us know where stars are being formed. But more importantly than that, we're also talking about the raw materials for planets and even life itself. Where are these small particulates? Where are they created? How do they get formed? How do they extend across the galaxy this way? And how do they clump together to make a rocky planet such as the Earth? And just to repeat that dust is a very small component of our galaxies, just tiny, tiny sizes. And in fact, the mass of dust in galaxies is negligible. It's less than 1% of the normal mass of the gas in galaxies. But yet it can actually absorb all or hide all of the visible light from a galaxy from our view. So we wouldn't be able to see anything using telescopes that look like our eyes. And I think one of the important things to remember is that when you look at visible light images, like using telescopes like the Hubble Space Telescope, you can get these phenomenal views of the universe. This is the Hubble Deep Field, a very famous image, where we have a very blank bit of sky. We've just stared at it with the Hubble Space Telescope, and we've just said, right, expose for a long time, see what you pick up. And what you see is a load of distant galaxies, some very far back in the universe's past, some stars in our own galaxy. And people thought, wow, this is incredible. For 400 years, we've been looking at the visible universe. This is now telling us how many galaxies we have out there. But what we didn't realize until very recently is that half of the starlight is being blocked by a dust grain. So let me say that again. Half of all the light emitted by stars since the Big Bang has been hidden behind a cosmic dust grain. And what happens to that light is that the dust grains absorb the light and then recycle it into a different part of the electromagnetic spectrum. So we can no longer see that with our visible telescopes. And so that's where the title comes from, the stolen starlight. The dust grains kind of steal it away and recycle it to a different part of the electromagnetic spectrum. And as I say, a huge amount of that energy is being hidden from our visible light telescopes. So the visible universe is only half the picture. To understand galaxy evolution, to understand planet formation, star formation, we need a telescope that also recovers that stolen starlight and looks at the emission from dust as well as the emission from stars. So we have had quite a lot of success in building telescopes in the past to search for that missing starlight, to look in that part of the electromagnetic spectrum where dust will glow. And that happens to be in the infrared part of the spectrum. So we just need to build an infrared telescope. It turns out, though, that that's quite technically challenging. We have an atmosphere that absorbs infrared light from space, so it's very difficult to do on the ground. When we get to space, we have to go very far away from the Earth to try and get away from the Earth because it is also an infrared light source. So we end up having to put these telescopes very far away. That becomes expensive. And the very sad thing about infrared emission is that you need to have a much bigger telescope for an infrared telescope to see the same level of detail than when you have a visible light telescope. So we would need to have the same level of detail as Hubble has. We would need to build a much larger infrared space telescope by a factor of tens to hundreds. So this is a really difficult thing to do technologically. But we do have some fantastic legacy instruments that have gone out into space and observed the universe at infrared wavelengths and tried to get that stolen starlight that we can't see with telescopes like Hubble. So this all started off in 1983 with the infrared astronomical satellite. And then we moved down the list to Akari, which is a Japanese-led mission in 2006. These are a combination of NASA, ESA, JAXA, and the French Space Agency, all working together to try and understand this missing half of the universe. And those did fantastic things, but they were unfortunately limited due to the technology that was available at the time. But I just like to have this slide because it makes me think we've had 400 years since Galileo where we've used lenses and mirrors to look at visible light, but it's really only been since the 1980s that we've had the technology to do the same in the infrared. So it's kind of recent when you think about it. The thing that I want to share with you today is some of the work that we've done with the Herschel Space Observatory. Now, this was launched in 2009 and stopped taking observations in 2013. And Herschel was a European Space Agency mission with participation from NASA. And Herschel was an £8 billion project that had a lot of leadership in the UK. So instruments were built here in the UK. A lot of the science was led here in the UK. And Herschel really revolutionized things because it had a big mirror. But it was at the time the largest single dish mirror in space, 3.5 meters wide. And so it gave us really, well, I wouldn't say really good details in images, but it actually is better than anything we had before. But more than that, Herschel did something really special, and it could see the universe in many different infrared colors. So what I mean by that, hopefully I can explain it, is if we want to look at infrared light, we want to look at infrared light that comes from dust grains at a wide range of properties, wide range of temperatures. Most of the dust in the universe is actually very cold. And by cold, I mean 20 Kelvin. But some of it is hot. Some of it is 70 Kelvin to 1,000 Kelvin. I'm saying hot here in terms of the infrared space. Certainly nowhere near X-ray emission. This is hot for a dust grain. So we need to build a telescope that can see the light that is emitted by objects at that temperature, just in the same way as that you can use an infrared camera to see heat within your house, or firefighters can use an infrared camera to search for people, the heat from people within buildings. So we do the same thing with space to recover that dust, to see that where the dust is. But Herschel was for the first time showing us how we could see all the dust in the universe. So let me illustrate that with a graph, if you'll allow me. Here we've got the brightness here on the y-axis, and then the wavelength of light that we're looking at. So visible light would be down here, and here we've got infrared light. And so what we had were quite a few instruments that would be able to observe hot dust at these very short wavelengths. So we're talking about below 25 microns. And if you extrapolate that onwards, you could say, okay, this is basically the feature that we'd expect dust to do. We measure the brightness at these different frequencies or wavelengths, sorry, and then we fit it with a curve, we can estimate how much material is there. That's how we get the mass of dust. That's how we know how what the mass of dust is in objects. Now that's great if we only care about hot dust, because that is only sensitive to hot dust. And in fact, to see the most of the dust in the universe, 90% of the dust in the universe emits at colder temperatures, which means we need cameras that look at longer wavelengths. Now, before Herschel, we did have that capability, but only up to about 160 microns. And what you can see here with this blue curve is that you are starting to see a similar shape as over here. You're starting to see a kind of increase in bump, but then there's no information on what's on the other side. Is it falling? Is it increasing? What's happening? So Herschel was fantastic because Herschel, as you can see by these little square boxes, Herschel took observations at many different infrared wavelengths or infrared colors. And because of that, we were able to see for the first time the 90% of dust mass missed in previous space telescopes. So it really revolutionized the way that we view the universe in the infrared. It really was an astounding observatory. And just to say again, there's about 1,000 times more mass in this bumpy emission compared to what you'd normally see at this shorter wavelengths. So getting that long wavelength information is crucial. Okay, so now that we have that, we have an instrument that can show us many different colors of infrared light. We can measure the dust masses that were too cold to be seen before. What does it look like? Well, if we take our nearest galaxy, Andromeda, this is just an image of the visible light, the starlight. So what you can see here is very bright center, and then there's these kind of hints at dust lanes in these dark patches that kind of extend through the galaxy. When you use Herschel, remember you're not looking at anything other than the dust, the glow from dust. So this is the starlight that's been absorbed by a dust grain and is then causes the dust grain to glow in the infrared. We get a complementary picture, or even the missing half of the light that we can't see with the visible telescope. And what you can see here is that where these lanes are dark in the starlight, you see that they are bright here in the far infrared, in the infrared dust emission. And you can see this lovely structure at the beginning. You can start to peer in towards the center a little bit more. And you can see that there's this very clear outer ring here. And we can use this information to not only combine the energy in stars and the energy in dust, which is the recycled starlight that we're not seeing in the other image, but we also can use the infrared emission to reconstruct what happened to this galaxy in the past. These rings and features and swirls around the center tell us a little bit about previous interactions with other galaxies. So we're finding that these images are not only showing us something we haven't seen in terms of where the light is, but also allowing us to estimate or probe the galaxy in a different way. So it's a really powerful thing to do, to have both those things together. Unfortunately, though, it turns out that when you actually do the equivalent of the Hubble Deep Field, so this is where you stare at a blank part of the sky, and just to give you an idea for scale, this is about 15 to 20 times the size of the full moon on the sky. So the full moon is your thumbprint. This is basically a few times bigger than that. And just by staring into a blank part of sky, this is the Herschel Atlas survey, which is led from Cardiff. And what we find in this image is that every single pinprick of light that you can see is a distant galaxy full of dust. Except for there's one towards the center, that very bright little blob, which is something that's happening in our own galaxy. But everything else you see in this image is a distant galaxy full of dust. The universe is incredibly dusty. And just to give you a bit of an insight into what the colors are telling us, the colors in this image, if it's red, it means it's either cold dust or very, very distant. In that case, the light is redshifted. If it's blue, it means it's hot dust or very, very close. So we now have this Herschel view of the universe, which is just showing us that there is dust everywhere. And there is dust in all galaxies that we can see out into the very early universe. That is a problem to explain. because there's a lot more dust than we realized. So where does it all come from? And that's one of the things that I've spent my research career trying to answer. Where is all this dust made? Bearing in mind that the dust emission is the building blocks of planets and potentially life itself. So it's a good idea to find out where these things are made. So what people technically, or what I was taught as an undergraduate, and what the textbook explanation of stardust and cosmic dust, and I'm sure everybody on this presentation will have probably heard this as well. The stardust is made, obviously, in stars. We come from stars. Our elements come from stars. And stars like the two here that are pictured are believed to be responsible for most of the dust in the universe. These are low to intermediate mass stars. So what I mean by that is stars that are less than 8 times the mass of the sun. These are the late stages of their evolution. So these are images of stars after they've gone through the main sequence phase, which the sun is in now. And beyond that point, they will puff off their outer layers. And as they do that, these outer layers, these stellar winds as they're called, are believed to be the perfect conditions for dust formation to occur. And if you think of dust formation as kind of like how snowflakes form out of the air, you just need the right temperatures, the right pressures. And if you get that right, then you can form solid particles out of the gas. And it's in these sources, these low intermediate mass stars, that it is believed most stardust is made. Certainly that was what I was taught as an undergraduate. And you know, that is something that we wanted to test. Now, we do know from infrared observations of stars like these are not infrared observations, I should have said, sorry, these are Hubble images. But we do know from images in the infrared of objects like these that they do have dust grains. They are creating dust in the universe, but they're not creating as much as we need to explain the Herschel observations of galaxies. So that's a real problem. It just doesn't add up. There's a dust budget problem here where the amount of dust we see in the universe cannot be explained from just the low intermediate mass stars that we have in galaxies. Just not possible. They don't create enough dust grains. Not only that, but it doesn't add up in terms of timescale as well, because if you look at the early universe, you see some very dusty galaxies. So this little postage stamp here is of a galaxy that's so distant, and all of this red and yellow emission that you can see here is dust and molecular gas. The amount of dust in this galaxy is not only huge, but it had to have formed within 500 million years after the first star formation. So as soon as stars were born in this galaxy, as soon as star formation kicked off, then within 500 million years, it must have had this much dust in. And the reason why we know it's 500 million years is because this galaxy is at a redshift 7.5. The universe was not very old at that stage. Galaxies didn't form at the beginning of the universe, they formed after the cosmic microwave background. So we have a time frame that we can say, hang on, dust must appear in the universe within 500 million years. Well, why is that a problem? Well, because the intermediate and low mass stars, just like our sun, take billions of years to get to their dust producing stages. So if these are the source of dust grains, A, they don't produce enough, and B, they take so long that we shouldn't see dust, the material for rocky planets, in the universe until a billion years after those stars are formed, at least, maybe even 10 billion years. So we're starting to see here that actually these can't be the only source of dust grains. So one of the things that I did, we asked ourselves in 2003, actually as part of my PhD with Mike Edmonds, who's the RAS president, we actually looked at whether a different kind of star stellar process, could produce the dust in the universe. And we thought, what is quick, what is rapid, and what has a lot of raw material that could turn into solid dust grains? What has a lot of iron and magnesium and carbon and oxygen and silicon? And for us, it was very simple. Could it be supernovae or the explosions of massive stars? We know they occur rapidly. We know that they are on timescales of millions of years, not billions of years. And we know also that they produce a lot of their own raw material. So if after the explosion happened, it could produce dust, then that would be a fantastic source of dust in galaxies. Now, the reason why this wasn't, this wasn't just us suggesting this, but the reason why it wasn't seen as plausible at the time, 20 years ago, is that the most consensus within the community is that the explosion of a massive star, the aftermath of that would just be too harsh an environment for dust grains to kind of, survive. So it would be too hot, million-degree gas. It would be too energetic, and dust grains would basically vaporize. We're talking about very little particles of soot and maybe a bit of silica. So it doesn't seem very realistic. But we decided to use Herschel to look and just check. Okay, so what we did is we took a couple of known supernova remnants, the aftermath of massive stars, and we decided to just look at them with Herschel. And if there's dust, we will see it, okay, because Herschel is sensitive enough to see it. And so we look at three different sources. Actually, there's four sources that I will talk about in this talk. The most famous of them being Cassiopeia A and the Crab Nebula, stars that blew up around 300, 400 years ago and 1,000 years ago in the case of the Crab. And then in 1987A, a supernova remnant in a different galaxy, which exploded in 1987. So if we just look at these with Herschel, what do we find? Is there dust in those or not? And that's quite an easy test to do. And that's what we did. So I'm going to just show you, whenever I show you the images of the supernova, I'm going to try and show you it with a visible light image, just so you can see the structure of the supernova as well as the dust that we see. So this image is the image of Cassiopeia A. The purple light that you can see is the emission from hot gas. So this is very hot shot gas that's the explosion and the material that was in the stars being moving outwards since it exploded and slamming into the surrounding medium. So the purple is hot gas, and the orangey red is dust that was seen by Herschel. And what you can see is that there is clearly dust in this supernova remnant. Not only do you see features that overlap with the well-known structure of the supernova itself, you see features within the middle. And if you work out how much dust there is in this supernova remnant, you get the equivalent of 200,000 rocky planets like the Earth. So in one explosion in our galaxy, we create a huge amount of dust. And we know that around one of these goes off every 50 years. So that actually would create a huge amount of dust, which would help our problem with the dust budget in the universe. So that's great. It's only one source though, so we need to look at others. If we look at the Crab, again, I'm going to show you the visible light with the dust emission. So the visible light here is in blue. Okay, this is the Hubble Space Telescope image in blue, but the Herschel emission is in pink. And what you can see is, again, there's a lot of dust in this image. We couldn't do this properly before Herschel, but now we can. And it turns out that in this source, there's only about 50,000 Earths worth of dust. This is slightly older, so it's not clear yet whether some dust was created and then destroyed. But either way, it's clear evidence that dust is formed in the aftermath of a supernova explosion. These are massive stars. This one is about 20 times the mass of the sun. Cassiopeia is believed to be between 15 and 23 times the mass of the sun. And so they are fantastic candidates because there's quite a lot of these stars in galaxies. I'm going to show you one which is a bit different to those two, G54.1 plus 0.3, very inspired name. When we looked at this one, this made quite a lot of headlines. What you can see here is the moving electrons in orangey red. That's actually synchrotron emission. And then there's this very bright spot in the middle, which is actually X-ray emission from the pulsar, from the neutron star in the center that's rotating. And then this greeny blue skirt is dust cloud that is associated with the supernova remnant. And we found a lot of dust in this source, 100,000 Earth planets worth. But not only that, we detected for the first time the signature of silica in the supernova remnant. And so this made a lot of headlines, which I'll show you in a second. And that was quite interesting because it's the first time somebody had allocated or detected the stuff that we find on Earth everywhere in sand, in glass, in concrete, was actually formed in a supernova, which is pretty cool. So finally, in terms of what Herschel saw, I want to talk to you a little bit about 1987A. This is the object that we saw that is in a different galaxy. Now, unfortunately, because of what I said earlier about the infrared lights, you need a very, very big telescope to be able to see details. As soon as you go away from nearby objects and you look in distant galaxies, you start to just see less and less detail, and things are more and more blobby. So this is the Herschel image here of this region of this galaxy where 1987A is. You may be able to spot this tiny little blob here, which is at the location of 1987A. So at the time, a team led by Mikako Matsuura postulated that this was dust in 1987A, and they worked out that this had 200,000 Earths worth of dust. So like Casset, but incredibly dusty. And there was a lot of controversy at the time as to, well, how can you tell this is dust in the supernova remnant? It could just be a dust cloud in front of or behind, or it could be around, and it's all just been smeared because Herschel can't see a good enough detail. Just to show you some of the headlines that we came from, some of the work that we've done on supernova and on dust in supernovae. But I've only shown you 4 sources, and no good scientist should say, I've discovered that dust forms in this source based on 4 sources. We should think, okay, there's 4 sources, they could be odd in some way, it could be a biased study. So how do we do something more comprehensive? How can we look at all supernova remnants and determine if they all form dust or if some form dust and some don't? So that's another thing that we try to do. And we actually got I feel very sorry for the PhD student we got in to do this, but we tasked her with studying all the known supernova remnants in the Milky Way that had been observed with Herschel. It was over 200 of the supernova remnants that she looked at. And what she found was interesting. She found that it was impossible to do this with Herschel. It's impossible to understand where dust is formed in our Milky Way because our Milky Way is too dusty. And so what happens is images are just too confused with dust everywhere. So here's an example of that. This image is a Planck image of the dust in our own Milky Way. You can see these huge filaments at the top here, of dust filaments extending really, top to bottom of the sky, and then very, very thick dust laying in the middle of the disk. And if you zoom in that area, you can now see a Herschel image of that region. All of the stuff you see in this image is dust emission. Again, the color tells you something about the temperature there. And you can see huge amounts of dust. And if we zoom in again, we just see a mess, just lots of dust everywhere. And it's very difficult to then say, is this in a supernova, in front of it, behind it? We have no distance information from dust emission. We can just see it. That's it. We don't know where it is in space. So that's a massive problem. And I'm just showing you this to show how painstakingly difficult her PhD thesis was. But she actually looked at all of the supernovae, over 200 supernovae, and looked at the Herschel data. And in every one of these postage stamps, you can see just how varied the emission is from dust and how difficult it is to be able to tell whether something is a supernova or if it's just some dust in a spiral arm between us and the supernova. And so we realized quite quickly, you can't do this on a statistical level. We are still stuck in the phase of only being able to look at individual sources, which is a real shame because you do want to learn something about, take the numbers that you observe and learn something about what that's telling you. We think about 38 of these over 200 supernova remnants may have dust signatures, but it's impossible to tell. So unfortunately, as wonderful as Herschel is, we're kind of at an impasse there. And what we then realized was what we needed was a telescope that had more details. So what if we had a telescope like Herschel, but much bigger so that we could see more detail in faraway objects, or even more detail in nearby objects. That would be fantastic. And it is a very difficult thing to do simply because the infrared light requires a much bigger mirror to be able to see the same level of detail. And astronomers got around this by building something called the Atacama Large Millimeter Array, ALMA. Okay, and ALMA is in the Chilean desert, and it's made up of 66 telescopes. And each one, most of them are actually 12 meters across, a few of them are a little bit smaller, and they look like this. So you've got all these dishes everywhere. And the magic of this is if you use these telescopes in a given configuration, you can take the light that you observe from every single telescope, combine it to reconstruct what you see on the sky. And these telescopes, individual telescopes acting together, are equivalent to an infrared telescope with a single dish that is the size of a small city. So the size of Cardiff, in fact. You've basically got something that is acting like a single dish that is 10 kilometers across. It's quite phenomenal as an achievement, the largest astronomical observatory in existence today. So ALMA allows us to get that detail, but it takes a very long time to do it. So you can't look at big objects or nearby objects. You can't really look at anything that's bigger than a certain size. But there is one candidate. If you remember 1987-8, then you may remember this blob where we believe we've seen dust emission. Well, ALMA has the ability to peer into that and tell us what is going on. And when we did that, we see this image with ALMA. Remember, infrared data is not often as pretty as visible data because of this issue, particularly with ALMA because of the atmospheric absorption. But if I compare our ALMA view here in this bluey reddy color next to the Hubble view here in this very bright red pink color, then you can certainly see the features of the well-known supernova remnant, this necklace of material here, this inner region here. Okay, those are overlapping. And what this allowed us to do, and what it allowed Mikako to do, Mikako Matsuura, is to prove definitively that the dust that Herschel had seen is actually in the ejecta of the supernova remnant here in the middle. This is the material that was in the star and is now exploding out and moving at very fast velocities. And that's where the dust is that we see in this glowing bit with ALMA. We can revise the dust mass down a little, but we're still talking about a significant amount of dust. Unfortunately, that's all we can really do with ALMA. We can only look at small things on the sky. We can't use it to map Cassiopeia A because it's just simply too big. It would take too long, and ALMA's not built to reconstruct very large scales. It's really for very small scales. Just to give you an idea that the distance here between the inner bit and this outer ring, we're talking about a few astronomical units, which I think is really mind-blowing. So we're kind of at an impasse again here. We now have a telescope that can do lots of details, but it can only look at a certain number of sources. Oops. So what if we had a telescope that could see more details, like ALMA, but also able to look at large objects nearby? So able to look at things like Cassiopeia A in more detail, because it's so big, it can observe it fine, whereas ALMA can't. And that's where James Webb comes in, the James Webb Space Telescope. This is really a technical marvel, a huge achievement for multiple institutes around the world. One of its major technical achievements is its mirror. As you can see from this picture here, we have very different mirror shape to a traditional. This is the Hubble primary mirror in comparison. So the Hubble primary mirror is often compared to a size of a bus. James Webb the mirror is the size of a tennis court. So that's the difference in the sizes. That allows you to collect more light. That allows you to see things further away, and it allows you to see more detail. And it overlaps a little bit with the kind of light it looks at. It does look at some of the gas, kind of just off the visible wavelength regime, but it also goes into the infrared. So it's brilliant for us as well. And just to say that this mirror was actually folded up inside the telescope and had to be unfolded in space. So this was a level of complexity that we've never really had to deal with before. And so technologically, it was a huge time coming. It was a long time to get this to this point. And it was launched in 2021 on Christmas Day. And since then, it's been breaking lots of having lots of scientific breakthroughs, but most importantly, making very pretty images, which is the thing I really love. So we've used this to look at our supernova remnants. And so far, we've got two that have been observed, and we've just recently, in the last couple of months, got the data for them. Just to say that the publications for these are not all published yet. They'll be coming out soon, but the images have been published by NASA. So for those of you interested, that keep an eye out on the archive for the papers that go with the images. But if we go back to our 1987A image, this is what we see with JWST, and it is absolutely beautiful. It kind of looks like it's out of focus, but that's not what's going on. What's going on is that there really is these multiple rings of gas and dust around this supernova. So if I just compare that to what we saw in Herschel, so I've zoomed into the Herschel image, this is the blob, okay? So there's just one blob. We're now able to see exquisite detail in the infrared. Not quite a fair comparison because Herschel is looking at longer wavelength light, but I still think it's wonderful that we now have an image of 1987A in the infrared, the image of the dust, which is so beautiful. And really, I should have compared it to Spitzer, but I've done it this way, just to be a bit unfair to Herschel. But what we see is a huge amount of structure that we couldn't see before, fainter structures, more detail, and different things lighting up in this image. So there's a really nice graphic done by the BBC for this. And what we see is these new outer rings that extend out here. We see this string of pearls around here glowing, this little bead of pearls. Those thought to be from mass loss that happened before the star exploded. So around 20,000 years before the star blew up, it shed a bunch of material. Okay, and that's what you've got here. And then what we've got that is completely unexplainable right now, these other structures we can kind of explain from previous mass loss before the star detonated. But everything within this circle and in the interior is really the ejector of the star, the stuff that was inside the star that is now being blown out into space. And we've seen these new structures that have been nicknamed the crescents, and we have absolutely no idea why they're there or what they're showing us. And that's really a fantastic thing that JWST is bringing to us, is new unexplained observations. However, it is also confirming that there is not only a lot of dust in the ejector, but there's also a lot of molecules, cold molecules, carbon monoxide, hydrogen, H2O plus. We see molecular hydrogen here, cold molecular laboratory within the center of a star that blew up only 30 years ago. And so it's really telling us that there's a lot of physics and chemistry going on here that we didn't have insight into before. And then finally, I just wanted to show you the image of Cassiopeia A with JWST. I think this is my favorite image so far. So this image is the color image. So everything you see here is observed by JWST. Some of it is glowing gas, some of it is glowing dust. So the glowing dust is this orangey red fiery. It looks like the whole thing is on fire to me. That is dust emission in Cassiopeia A as seen by JWST. And again, we're seeing a view that we didn't see before. We're starting to see, you know, for example, why are these dust features here? You know, what are these dust features here? Is this maybe dust swept up by the expanding supernova remnant? Is it dust that existed previously? Is there dust inside the ejector? We don't know. And the exciting thing that we're currently really busy writing our papers on is this thing in the middle. Whoops, this thing in the middle here. So just zoom in. This is nicknamed the green monster. And there's absolutely no idea what this structure is or how it came to be. But we know it's bright. It has a lot of neon atoms in there, or ions, and it has a lot of dust emission. But why it looks so different to the surrounding dust emission, why it's a different color, which means it's a different temperature, we have no idea. And this is something that we're looking forward to exploring. So just to wrap up, I said at the start that we are all stardust towards the start, and that's true. I think it's it's obvious that we are made up of the elements forged in stars themselves. But what we're starting to learn about the universe is that there's so much of it out there, and that it is created very early on after the first stars are formed, and that maybe perhaps most of our stardust comes from a different source to the textbooks. So I'll just finish by saying we are all mostly stardust from the titanic explosions of the biggest stars. And thank you very much for your time.
And thank you, Professor Gomez. We do have quite a few questions. If you have any more, you're welcome to post them into the chat. I'll give you a few now that we have. Let's see here. Just going to switch to there. There we go. Okay. Very interesting questions as well. One question David Walmsley asks: how many galaxies are visible to us at the moment? I would say there's quite a few, or I guess wonder what he means by how visible. But anyway, go ahead.
Yeah, I guess that's so in terms of if it's visible in terms of the starlight, then we know, well, there are millions that have been observed with telescopes and surveys, large surveys of the sky. For example, the well-known 2DF survey, which observed, one of the first surveys to show large-scale structure in the universe, with lots of galaxies kind of structured in this web shape. So we know of millions of galaxies that are visible in visible light. In terms of the infrared, that's an interesting question, because I'm trying to think what the statistic is. Not all of the sky has been observed in the infrared. With Herschel, I think we got probably about a few hundred. Sorry, let me think. Couple of, I would say about 100 square degrees is what we observed in the sky. So not all of it, but quite a big chunk of it. And we know from looking at pulling out galaxies in those infrared surveys that actually there's, again, millions that we can see in our infrared telescopes. So yeah, of order of millions are visible to us in terms of what we've observed. But there are many more that we're missing because our telescopes aren't deep enough, or we haven't looked at that part of the sky, or our telescopes maybe clump lots of galaxies together. So just like that blob with Herschel, you just see a blob instead of 3 or 4 galaxies in a very small space. So there's a lot that we haven't seen. But yeah, we're talking order of millions.
Yeah, that blob that Herschel took, and then next to the JWST image was a huge difference. I just is a lot of the time of this is my own question now, out of curiosity. A lot of the time of JWST looking at maybe those fuzzy images from Herschel, that astronomer goes, oh, you know what? I would really like to see that a little bit better. I mean, JWST is it spending a lot of time doing that, or trying to look at new parts of the
Oh,
sky?
that's a good question, Lucinda. That is a very good question. So I think the answer to that is generally no. It's mostly doing discovery science. It does look at nearby objects that we've seen with Herschel that are kind of like legacy objects. So 987A is a legacy object. It's a supernova that's blown up in our time. We know what star blew up, so we can follow it through. And so JWST is going back to that source to kind of get that, not only that better view, but also to see things that Herschel couldn't, like, for example, those molecules. And so it has both photometry and spectroscopy capabilities. So we're able to do that and do new science with it. So I kind of would say it's revisited some famous objects that Herschel's already looked at, but it has additional science. But then most of the JWST, I would say, is doing its own science for its own sake. Yeah.
And you brought up another really interesting thing about astronomy, and the molecules that are created in space are things that we couldn't even create on our planet, in our atmosphere. And I don't know if those are the things you look at all, but you're looking at the things that we're familiar with. but it's mind-boggling and interesting to know that chemistry could be actually so different in space and those temperatures and things.
Absolutely.
Yeah, just curious.
Absolutely.
Okay, get back to the attendees. Thank you for being here. Here's a second question from Adam Rollinson, who asks, what kind of mass ratios do these large volumes of dust have? Apart from the obvious effects of light obscuration, extinction, does interstellar cosmic dust have any significant gravitational effects on stellar masses, or is it still far too rarefied? They ask.
Oh, yeah. Okay. Yeah. So, good question about the mass ratios. I'm gonna answer the second one first, the gravitational masses, the gravitational effects. It has very little effect on gravity because the mass of all the dust, if you take our galaxy, which is chock full of dust, if you take that up and you add up the entire mass, it's less than 1% of the mass of the galaxy that is not in stars. So if I put that another way, you have stars, you have gas, you have elements in the gas, you have dust, you also have dark matter. And dark matter and stars are way more massive than the dust emission. And the dust emission is only 1% of the the gas, the gas itself. So you're talking about a tiny, 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 tiny fraction of the mass of a galaxy. So if the dust is in front of a background distant galaxy, and you're talking about gravitational lensing, dust dust will affect it slightly by making it a bit dimmer, but it wouldn't affect the gravitational. It wouldn't affect the reconstruct. Sorry, I'm not saying this very well. So it wouldn't actually affect the what what gravitationally happens to that light. It would just slightly dim it. It wouldn't change the way that the the gravitational effect itself will make us see something like an Einstein cross. That would not be affected. It would just be slightly dimmer. Um, in terms of the first question, it's not. I'm not entirely sure what the volume ratios mean. But there are some galaxies where you have so much dust you cannot see the visible light. So there are some galaxies where 30% of the light is in the infrared, and 70% is emitted in the starlight, roughly. Some where it's more like 90% in the infrared, and some where it's 100% in the infrared. Well, it's not strictly 100% infrared, but it's so much of the starlight is obscured by the dust emission that we can't see that with a visible light telescope. So it's and sometimes, as we saw in those images, it can extend across the entire galaxy. So it can be, you know, if you look at a distant galaxy, then the you could have a dust screen, kind of a smoke screen, as I like to think about it, cosmic dust lane that blocks out everything that we can see. And it's only if it was possible to take your telescope inside behind the dust screen would you be able to see what was inside the galaxy. So I hope that answers the question. I'm not sure if I got the volume question right. So feel free to respond.
Yeah, if you want to add more about your question in the Q&A, please do. If that wasn't enough, but I thought it was really great. Thank you. It brings up a lot of, it's some of the things that you brought up in your talk. And again, I'm going to speak from my own out of interest here, that the Milky Way is too dusty to study dust.
I know, it's such a pain.
And also, when you see dust that you're looking at, it's not really helpful. You're trying to find something isolated with nothing in front of it or behind it
Yeah,
in order to be able to study the dust it looks like. And it was just amazing. You showed this image of this whole dusty area that looks like, I guess, dust, and there's only like one point in it that's good enough to look at.
yeah.
Why is that?
Um, so what you've got is the problem that because you want to know whether it was formed in the supernova remnant, you have the problem that if there's spiral arm or a star formation cloud or a ionized hydrogen region, lots and lots of things in space are cocooned in dust. And that's one of the reasons why it's so important to study, because it's important in so many astrophysical processes. But there's just so much there that when you when you want to ask yourself, okay, how can I prove that this is actually supernova dust? You need to have those very clear images that we got from ALMA. Um, or if it's very close and nearby, then it's automatically big and you can see structure in a really good way. Another way to do it is to compare with the X-ray and the radio light that comes from supernova remnants, because they are from the supernova remnant. They're not from a different source. They require very energetic processes, so they're more rare than dust. So if you see an X-ray source where you think a supernova is, then you're pretty sure that's your supernova. If you see dust, you have no idea if it's in front or behind or in the supernova remnant. So even if we could do ALMA, if we could use ALMA to look at every source in our galaxy, then we might be able to deconstruct those different options. We might be able to rule out some options for the dust we see, but it's expensive to do that, and ALMA is just not capable of doing nearby things that are bigger in our own galaxy. What it is capable of doing is distant things. So if there are more supernova remnants in galaxies like the Large and Small Magellanic Clouds, then maybe it's capable of doing that, but none of them are as bright as 1987A. So it ends up being very expensive in terms of ALMA time, and frankly, just not really worth it. ALMA's much more suited to do other things. So it is a bit of a shame that it's now at the point where in our own galaxy, where we're supposed to be able to see in detail, we can't actually do that. But what we can do is go to nearby galaxies and maybe use ALMA for that. It's not sensitive enough to go further.
Yeah, that's just really mind-boggling. It's interesting. Um, and of course it's about getting the data and having, the good data. You don't want anything messing with it or interfering with what you're actually trying to study, and that makes a lot of sense. Okay, a couple of questions from Kang Lee. Really good question about what causes the differences in temperature of dust particles. That reminds me of going to university and astronomy.
Yeah, yeah, that's a really good question. Something I didn't explain actually in our in the lecture, but it's basically the what it's been heated up by. So if you think about yourself, right? We sit in the universe, we sit on our planet, and we have a body temperature, and we emit light in the infrared, quite short infrared. Now, when dust is in a galaxy, it can be heated up by a nearby star that's very massive and has a lot of energy. It could be heated up by um, some ionized gas that's nearby, or it could be heating up because it's surrounding a star that's beginning to form, and fusion has started and started to heat up the gas and dust around it. So whatever is heating the star will then partly determine the temperature that whatever's heating the dust will partly determine the temperature the dust sits at. Another reason for the dust temperature is the size and the composition of the dust grains. So you will have a different dust temperature if you have glassy dust grains or gems than if you had a sooty dust grain. And so they will absorb the lights slightly differently to each other and then emit it differently, and that will mean it'll have a different temperature. So it's about the heating and it's about what the dust is made of, and what we do, or even how far away it is. So when we talk about galaxies, if it's really far away, the light will be redshifted, and that means that the dust will look red in our images, and that means that we might think it's colder, but it's actually not colder, it's further away. So yeah, it's a little bit of physics called black body radiation, and dust grains are just like us. They absorb energy, they absorb light, and then they re-emit it. We glow in the infrared, dust grains glow in the infrared, and their temperature just depends on how hot their surroundings are and what they're made of.
Excellent, really good question and good explanation. Thank you. Kang also asks, how were scientists able to isolate and study stardust found in the tail of comets? So I don't know if we get ice and dust in those as well. And why was the stardust able to fall down to the Earth's surface through the atmosphere?
Oh yeah, good question. So I'm going to blow your mind now. Around 40,000 tons of dust from comets and asteroids falls onto the Earth's surface every year. Okay, so a lot of dust falls out, um, falls from space and enters our Earth's atmosphere. So it's just because there's a lot of bodies in our solar system. There are a lot of dust grains in our solar system. We know of a lot of comets and asteroids, and every time they kind of fly by, then we might get a sprinkling of dust that comes down. So we have a lot of stardust that we can actually observe. I think there was a great experiment recently that had little collectors on skyscrapers, and they kind of collected stardust and showed that that was actually from the supernovae that we've been talking about. So another way to prove that supernovae are responsible for making dust. Now, in terms of how they isolated it, they basically used something called aerogel, and they it's kind of like a clear, slimy, jelly type material, which they flew through the tail of the comet, and the dust particles in the tail of the comet got stuck in the aerogel, and then they brought that back down to Earth and were able to then investigate what the dust grains look like. And I believe there was a recent mission with collecting cometary material as well. So there's a lot of information we have of getting hold of the dust and being able to look at it on Earth, which is really lucky. I mean, it's great that we can do that. Of course, that's solar system dust. And what we don't have much of is what we call interstellar dust, which is the dust that is more prolific in galaxies. And that dust is very rare in terms of coming into our solar system. So most of this is probably a little bit biased because it's the dust in our solar system. And we already know that our Earth is very rich in minerals. We have a huge amount of silica, for example. That's not that common. So we have a very rich planet in terms of minerals and metals. And so our solar system dust is also quite rich, but it's a way of viewing, of extrapolating to what we think dust in other galaxies might be made of.
Really great. And it's so interesting. We're getting lots of really great questions, and just people are saying, "Great talk. Thank you so much." And I'm going to end with this last question from David Walmsley, whose daughter is also watching you right now. And he says, "Thank you for a great talk. My daughter loved it. She has one last question, and this is the ultimate question we always get. Sorry, can you guess what it's about?"
Black holes. Yeah. Okay.
So,
Yeah.
does dust block out other things such as black holes? And
Yeah.
someone talked about dust on YouTube as well, wondering if you could get rid of it with high powered lasers, maybe.
Do you know what? It's actually that's a really good question as well. So in terms of black holes, uh, there are dust disks. So these circles, almost like a donut shape of dust that surround the black holes at the center of galaxies. Okay, so right at the center of galaxies, you have these supermassive black holes, and we sometimes see them when they're in their active phase. We call them active galactic nuclei. And what you see around these active galactic nuclei is this beautiful skirt of very thick dust. And one of the theories that was put forward before Herschel was launched is whether or not the presence of a black hole and this material that is kind of going around the black hole, this accretion disk it's called, and then this dust disk that goes around with that, whether that actually is a way to form new dust grains. So the dust wasn't sucked in towards a black hole, but rather was created there. And that's very hard to test. Nobody has a really a good idea about how to test that. But we do see lots of dust around those supermassive black holes. We don't think it's strong enough to block out small black holes in our own galaxy, because we normally observe them using X-ray emission. And so X-ray emission can penetrate dust quite easily. In terms of laser beams and destroying dust, dust is quite easy to destroy. It can be vaporized. So just imagine a lump of soot in your log burner, and you just turn your fire's very hot, the soot just disappears. You've got it can collide with each other, that smashes it up. into smaller pieces, which are then easier to vaporize. And you can do lots of different things where you can destroy dust quite easily. I'm not sure about the laser, but it's certainly quite an efficient process in the universe, which makes this question of where it all comes from even worse, because it's quite easy to destroy. And by destroy, I mean just return it back to the gas phase. So it's no longer solid, it's no longer stardust. Um, and yet we see so much of it out there. So that's quite a weird situation to be in.
Well, what an interesting and fantastic talk. Very just amazing. Thank you so much, Professor Gomez, for being with us. I really appreciated you spending time with us, even if online. I knew it was told it was going to be very special, and it really was. And confirming, all the song by Moby that we're all stardust, or what the largest stars. I think you said the most
Yes.
massive stars. Yeah. Well, thank you. If you just take a moment, and I'm going to wrap up here, and you can think about maybe if you have any last words before we say goodbye. I'll come back to you in a moment. In the meantime, thanks to our speaker. Thank you for still being with us today. And I just want to mention that our next public talk will be December 12th at Burlington House. It'll be a hybrid meeting with Dr. Naomi Rowe Gurney, and she'll be giving us, which has become now our annual Christmas treat, a JWST update. Like Professor Gomez mentioned, it's just the beautiful imagery that we're getting back from this amazing telescope. So thank you. And if you have any last words, anything you want to leave us with, Professor Gomez?
I just want to say thank you so much for the wonderful questions. Those are really, really amazing questions. So thank you so much for your time and for listening and for contributing to this really engaging session. Thank you.
It was. Thank you. And thank you. Okay, bye everyone. Thank you.
Bye.